All right, so hello everyone. Welcome to the IEEE Big Data Analytics tutorial series. This is Qiu Shi. Today we're honored to have Professor Enrico Zio from Paris PSL University and Politecnico di Milano. The topic today is data-driven prognostic and health management for the predictive maintenance of power components and systems. The increased knowledge, information, and data KID available today can improve our prediction capabilities, offering new ways for the reliable design and safe operation of energy components and systems. Particularly, the increased availability of data coming from monitoring the relevant parameters of the component systems and assets performance, and the growing ability of treating this data by intelligent machine learning algorithms capable of mining out information relevant to the assessment and prediction of their functional state have opened wide the doors for improved design, operation, and maintenance. In this webinar, Professor Zio will look into this from the perspective of data-driven prognostics and health management, PHM, for the predictive maintenance of components and systems of the energy industry. The talk today will be 1 hour or so, and during the talk or after the talk, you can feel free to send your questions to me through the chat box. And now I'll give the speaker to Professor Weng. He will have brief introduction of Professor Zio.
Thank you, Qiu Shi. On behalf of the big data community from IEEE-PS, I would like to welcome Professor Enrico Zio to give this talk. He got his PhD from nuclear engineering from Politec Milano in probabilistic risk assessment at MIT in 1996 and 1998. During his career, he got numerous awards. For example, there's a Hublot Research Award, and there are outstanding lecture from both IEEE and Sigma X Society. He also got awards, and that is on risk and resilience assessment. I guess this will be a key part of today's presentation. We can focus on that part when we are learning from him. And his Google Scholar is pretty high. That means, for the students here, you probably want to look into the paper and see whether this is very exciting for your work. And in 2021, he has been appointed for several very important positions. For example, the member of Broad Committee of International Joint Research Center for Resilient Infrastructure, 2021 to 2026. The others includes 40U and also Prognostic Health Management Society for his contribution on maintenance. Finally, I would like to conclude the introduction with his view and his position in 2023. He has been appointed as the scientific director of research and development Datrix AI Solution Group. So that is tremendous knowledge for us to learn from him about power system failure, repair, and maintenance. With that, I want to thank you again. Enrico, we look forward to your talk.
Thank you very much. I would like to thank the organizers for giving me this opportunity. And of course, I thank very much already the audience for the patience of listening to this talk that was, titled Data-Driven Prognostics and Health Management. And I right away wanted to introduce the KID power, okay, the knowledge, information, and data. So, of course, we're talking about power components and systems. So we have our power component or system, okay? We are measuring some data, okay? And actually, here's where the KID comes out. Nowadays, we're not just measuring numerical data on components and systems, on power components and systems. We're also taking images. We are also writing reports, inspection reports, operations reports, safety reports with respect to their behavior. And we also have a lot of knowledge, let me say, embedded in physical mathematical model that describe the evolution or the response of the system, the state of the system as a function of time, solicited by a number of factors that influence its behavior. So we got this kid in our hands, and what we want to do is actually to manipulate that with some algorithms, and typically now we will be talking, and everybody's talking a lot about the power of artificial intelligence to exploit these data and actually exploit this kid for specific purposes. And in particular, in our case, we really want to characterize something about the system behavior, the component behavior, about the state of the component and or system, estimate how is it doing at a certain time, and even more ambitiously trying to predict its future evolution. This ability to squeeze out from the kid some relevant knowledge on the system state, current and future, is at the basis of the so-called PHM, the prognostics and health management, whose main tasks are to enable, thanks to the estimation and prediction of the component and system state, enable the task of detection of anomalies of behavior, of malfunctioning, of degradation in the component or system, diagnosing what is the cause, what is the problem behind these anomalies or malfunctions, and even predict how and when these anomalies, these degradations are going to lead to a failure of the system or component. Of course, this is quite relevant because then this would allow us to inform our decision on what to do about it. Okay, we are estimating and predicting a degradation evolution. We are predicting when the component might actually fail, so we can take an informed decision on when to do something, for example, substitute the component or inspect it and repair. Excuse me. Now, the issue of maintenance, of course, is not a new issue, and there's been, in a sense, a rational development of how have we been dealing and how are we dealing with the maintenance issue. When productions and services were not, I would say, concerning a mass population, the few failures that we were encountering on the production systems, on the products themselves, were dealt with a corrective maintenance, a repair. The component fails, we repair it, okay, and we have the patience to wait for the repair conclusion. Of course, with the mass production and the mass services, this was not acceptable anymore, because now failures in products, failures in production systems, failures in service systems would really affect many people. And so we moved towards scheduled maintenance, trying to define when to do something on the components so as to arrest, mitigate its degradation, prevent failures, so intervene before failures. And of course, you are at the present time and you got your critical component, which of course it's a wine glass. I mean, a wine glass is a critical component in many countries, and certainly in Italy and France, and you certainly don't want it to fail. So you are acting with some maintenance in order not to encounter the failure of your wine glass, because that's quite important. And it might be a situation where the failure time would have occurred quite some time after you actually maybe replaced the glass of wine. Now that would be a pity. I mean, this is a lost drinking time that is really a pity to give up. So the ideal situation would be that you are at the present time, in some ways, you know when the failure time of the component will be, so you are able to predict the time at which the component will fail, and therefore you really replace your glass of wine just before failure. In this case, you would exploit completely and have fun at the party. You would completely and fully exploit the life of the component, and therefore you would avoid some unavailability periods due to unnecessarily early maintenance. Okay, and this is really what you are shooting at with predictive maintenance. Of course, the failure time, the time at which the component will fail, is uncertain. And from a statistical point of view, you typically have a distribution, a probability distribution function that describes this uncertainty on the time of failure of the component. Now, when you're trying to estimate the failure time of the component for scheduled maintenance, you run into two risks, let's say, okay, given all the uncertainty inherent in the randomness of the degradation behavior of the component or system, and also in whatever technique and model you're using to estimate the failure time, to predict the future evolution of degradation up to failure. So these uncertainties may lead you to make choices of when to do maintenance too conservatively. Okay, so a too early prediction, like we mentioned before, a long period of lost drinking or lost usage of your component, or even worse, a too optimistic prediction of your estimation, and so you're actually making a late prediction of failure, and you encounter a catastrophic failure, which typically requires a much more and longer period of repair, and depending on the component, it could be catastrophic in many senses, not only in terms of lost production, but also in terms of costs and even environment and public or work consequences. So the problem of prediction then has evolved and is evolving because of the evolvement or the evolution of technology from different perspectives. On one side, of course, you had the great evolution and development in sensing technology, where nowadays our systems and components are quite censored for monitoring purposes and for control and operation purposes. So there's a lot of available data that nowadays we are able to more and more use, more and more interpret, more and more analyze, thanks to the incredible development on one side of, let's say, data analytics, and of course, machine learning, artificial intelligence is a big part of that, okay? Enabling to squeeze out relevant knowledge from the data collected by the sensors that are monitoring the state and the responses and the behavior of the components and systems. And on another side, of course, the computational capabilities, which have increased tremendously. And this combination of availability of data, ability of analyzing the data, and ability of computing has enabled the concepts and the techniques of condition-based maintenance, where you are at the present time and you are able to extract some knowledge of some degradation indicators, and you realize that at the present time you have arrived at a certain level of degradation with respect to the failure level, okay, which suggests you and encourage you to intervene on the component or system because with all the uncertainties in the future evolution, the level of degradation is too high to take any risk of too late maintenance. So you enable detection and diagnosis, and you decide to intervene with some type of maintenance. And even more ambitiously, as we mentioned before, you actually are at the present time, and with the data available and the information available on the past behavior of the component and on its level of degradation, you can actually project the future evolution of the degradation of the component, so that you can estimate when it would fail. So we really are pushing the prognostics and health management all the way to prognostics by predicting the remaining useful life. And so you have a knowledge of the time span, the grace time within which you can actually organize and deploy your maintenance. And this, of course, can be updated dynamically, and you can decide based on a prediction of the remaining useful life when it is best to intervene with a repair, a replacement, a cleaning of certain kinds. Now, why are we making a big deal of maintenance? I mean, is that a big deal? Actually, maintenance is a big deal. Maintenance is a very big deal on all production, manufacturing industries, okay? Here I throw you a couple of examples on energy and mining, okay, where the costs of maintenance are significant. And when we talk about costs, we talk not only about direct costs for doing the replacement of the parts, for having the resources to make the inspections and the maintenances, but also we're talking about indirect costs, where we might pay a high price for a non-efficient maintenance and for encountering failures due to a lack of maintenance. Now, this is quite important in several, if not all, production and manufacturing industries. And the predictive maintenance part itself is really a big market. There's a lot of interest within the concept of Industry 4.0, where the digitalization of industries and also the robotization, automation has enabled predictive analytics to support industrial operations. Okay, well, maintenance is a big deal. Predictive maintenance is a big deal with a quite interesting market if we want to monetize the impact of predictive maintenance in our industries. Now, this is also seen from the point of view of research, development, and deployment of prognostics and health management for predictive maintenance, okay, where you notice a significant increase in publications, okay, on the theme of prognostics and health management for predictive maintenance. And you find from the academic side a lot of developments of efficient methods and techniques for all aspects of that enable prognosis and health management, the treatment of data, the extraction of relevant features of the data, the models for diagnostics and prognostics, and the optimization of the decision informed by on maintenance informed by the prognostics and health management tasks. And on industry, you see also quite an interesting focus on what is the requirement for prognostics and management. How do you deploy it in terms of architecture, design, and installation, the software and hardware that you need, the return of investment that would drive an effort of prognostics and health management for predictive maintenance. And of course, this applies to very much to power industry, okay, but not only to the power industry, okay. For example, mobility systems are intensely looking into and deploying actually solutions for failure detection, degradation detection, diagnostics, and even an attempt to push the predictive modeling for predictive maintenance. A couple of examples maybe I've taken also from these areas. Now, this is all nice and beautiful, but if we go down to seeing what we are dealing with on the field when we are taking components and systems and are trying to handle their characteristics for extracting relevant knowledge to enable detection, diagnostics, and prognostics, and eventually arrive at decision-making on terms of predictive maintenance, things get rough, things get interesting, okay? First of all, our systems nowadays are quite complex, quite performing, okay? But they're quite complex and made of a large number of components whose logics and operation are highly interconnected. And of these components, we measure a large number of data, of signals, of parameters, as I said, for controlling their operations, for monitoring their states, okay? So we're dealing with big data because of the numerosity of the signals that we're measuring on a plant, on a production plant, okay? And also because of the frequency with which we are collecting this data, that for some types of components and for some types of systems is done at a very high frequency. But it's not only data. Nowadays, on structures, on systems, on components, we are also exploiting the opportunity of collecting images. Nowadays, even in some structures and components and infrastructures, through drones, through rovers that go out and take images. Here you have some examples of X-rays on welding of pipelines to see if there are defects or degradation points. You have a thermography of an inverter for a full electrical vehicle, where you see hot spots of stress concentration, which may suggest that there are some degradation. You see also some images taken from lots of production of wafers for the semiconductor industry, where depending on the pattern on the wafer map, you associate to that different states on the wafer before you put it. Let's say you license the lot produced and the production itself, and send it out to the market. Okay, depending if it's healthy, if the map shows a healthy pattern or some anomalies which you want to then diagnose to find out what's wrong in the production process. So we got also images that we can take advantage of, and we also have more and more I would say the desire to extract also all the knowledge on the state behavior, evolution, response, and the maintenance of the components and systems in terms of the reports that are filled and written by maintenance teams, by operators, when they record an inspection, when they record a maintenance intervention, when they record an incident, an accident, a near miss. And here you have some example on maintenance records for the mining machines, equipment. You have some reports on, again, in inspections on mobility or train systems. You have safety reports on incidents occurred in some oil and gas plants. So this is motivating us to talk more and more of not just big data, but big kid, big knowledge, information, and data. And this makes us ambitious with respect to what we can do, what we can extract from this big kid. Now, so we got in our hands a big kid. The characteristics of the components and systems are also such that in certain instances and certain industries, you are operating and maintaining fleets of similar, if not standardized, systems. Turbines, airplanes, engines, airplanes themselves. So standardized equipment, similar equipment, which is installed in different areas of the world, operated in different ways, maintained in different ways throughout the world, throughout their lives. And you're collecting the kid on the different instances, the different components in the different plants, and centralizing this knowledge. And you want to make use of all this knowledge of these different units or different systems. These systems are as similar as you may imagine, but they are under different conditions, operated environmental conditions, and also operated in different ways. So the same component is actually behaving somehow differently, and in order to exploit the common characteristics and even the different characteristics or different behaviors that they have, you need to somehow be able to transfer and look at this different data in the right, let me say, in the right space, so that they confer to you relevant knowledge about what you want to know on your type of system, on your type of component. This will come back a little later, I hope, in an example that I will have time to discuss. And not so different standardized similar components, but in different environmental operating conditions, and also typically throughout the life of a component or a system, things change. Things change because elements of the system change. For example, it's the same component, but the plant is experiencing different events throughout the life because there is an undetected leakage in a certain valve, and then it is detected and maintained, and then there is an upgrading on another component, for example, an heat exchanger. And so the same element is playing in a team that changes and in different conditions of the team. And so the signal that you're monitoring on its state is changing. It is not maintaining the same throughout the lifetime. And your modeling efforts, your data analytics effort for detecting anomalies, for diagnosing failures, and for predicting failure times needs to account for this evolution of the component and system. Even nowadays, a lot of interest is also in the effect of climate change on the behavior of some components and systems, and the effect that it might have on their degradation. So this is something that needs to be taken into consideration. And if you think about it, let me just close here 1 second with a consideration. If you think about it, it's like the human beings. There's a lot of similarity among a certain segment of the population that lives in that has a certain age, a certain history of life, in different areas of the world, and it's experiencing changes in its in her or his life. Okay, and you want to, and you are a doctor, and you want to exploit whatever data information is available on this history of the individual persons, okay, in your population, to characterize relevant knowledge for detecting something that is anomalous in your specific patient. You're the doctor that is taking care of certain patient, okay? So there's a lot of similarity with respect to that. We're trying to build a doctor for power components and systems, and the opportunity is to exploit as much as possible the knowledge, information, data that we have, okay? And we want to exploit it as much as possible to guide, to inform in maintenance decisions in a predictive way, making the best out of the kid. So, of course, there is an aspect of information and data collection, which we have already, in a sense, mentioned. Okay, is taking in the big kid. Okay, and really, these are the ingredients for the efforts of predictive maintenance that we want to use for informing our maintenance decisions. Just as we said before, okay, not just numerical data, but signals, sure, but also images, text, and whatever we can use to draw some relevant knowledge on the state behavior of the component or system. And in fact, then we move to the feeding of these ingredients in some cooking pot. In particular, nowadays you hear a lot about artificial intelligence, machine learning as a proper cooking pot for these types of kid available. And the knowledge that you extract, the plate, the food that you get out needs to be relevant for the purposes that you are seeking, okay, in terms of detection, diagnostic, and prognostics in our specific case. With that, you go to informing decision making, okay, and taking the decisions of what to do on your component. Informed very well by the information, knowledge, and data that is available on your component. Now, the development of the prognostics and health management for predictive maintenance is an intense journey that industry needs to make, that of course starts from questions at the design level of what is the prognostics and health management that we need to do for our particular component or system, for our particular production or manufacturing system. How do we obtain that PHM that we want, okay, with the specific requirement that we want and the return on investment that we expect. And that's when you go in the actual methods for processing the KID and enabling the prognostics and health management tests of detection, diagnostics, and prognostics. And then how do you use the anomaly detections, the diagnostics, the predictions of the remaining useful life to feed, to inform, to feed the actual predictive maintenance decisions. And without getting into too much details, this, of course, first of all, implies answering some very specific questions, okay, of requirements on the PHM system that we want to develop, on how to assure that these requirements are satisfied throughout the use of the PSN system during the life of the component. And here is again the issue of evolving environment, of the changing of the components behavior, and therefore of the signals that are monitored, and the guarantee that the models can follow also these changes and still provide you the sufficient accuracy, the expected precision for your purposes. And then eventually I get these predictions. How do I embed this in my decision-making optimization problem of making the best maintenance at the right time? So doing the right maintenance at the right time in the right way, which opens up also the aspects of taking into consideration the demand for the product, the peak hours of production, and other aspects, the weather conditions for certain aspects, and other things. And we'll come back to that towards the conclusions. This, which is nicely put in, let's say, a series development, a series process, design, development, and decision, actually is much more complicated. I will not go into the details, but there's of course all kinds of feedbacks between the definition of the requirements, the development of the prognosis and health management solutions, what must be done to enable decision making for the maintenance actuation, and so on. So the engagement for developing predictive maintenance is not just a snap of fingers. Okay, it's really something that needs to be processed in a very systematic way in order to be effective in all senses. Now, when we go back to components and systems, one thing that you need to first of all do at the industrial level is to, of course, decide on which components am I going to focus my efforts of prognostics and health management or predictive maintenance, because they're costly on one side, and then they need to be effective. Am I going to put my efforts everywhere on all components or not? Well, typically then here you make some engineering rational analysis to identify which components most deserve your attention. And typically, you look at the typical, let me say, risk map, if I can call it that way, for the possible damages that the failures of a component in a system may lead to, and the frequency of occurrences of these potential consequences. And of course, you have different situations where when you have situations where the loss of a component is bringing very large consequences of all kinds, production consequences, production of time, economic losses, even potential environmental and injuries or fatalities, and it occurs very frequently. Then, in this case, there's no predictive maintenance and no PSM to be done. I mean, you need to solve the problem at the design level. That system cannot be operated with a component that actually is so critical. If the component is frequently failing, but the losses and the damages are not so large, it's bothering. It's bothering, and so depending on the real impact that it has, you can either wait and just repair, because the losses and the damages are not significant, or since it's bothering, you can schedule the intervention. If the component failure leads to consequences which are not very significant, and actually the failure occurrence is rare, you might as well, just wait and do corrective maintenance. There are then relatively rare events of failures of components that, however, lead to large, let's say, catastrophic consequences. But catastrophic, again, can be from a safety point of view, from economic point of view, from production point of view. And this is just, you cannot take the risk. Yeah, okay, we understand it's not frequent, but you want to monitor the situation. And it's in that situation where the most value is coming from condition-based and predictive maintenance supported by the KID. Okay. Of course, once you have identified that component critical for those reasons, let's go and do predictive maintenance. Well, do we have signals that we can monitor that speak to us about the degradation process, about the anomalies in that particular component? Because if you're not measuring anything on that component or anything that relates to its state in terms of degradation, in terms of functionality, okay, then we have our hands tied with respect to the possibility of detecting, diagnosing, and predicting eventually failures. Okay, and then detection, diagnosis, okay, usually possible for the prediction. Okay, and to go towards prognostics for predictive maintenance. You are extrapolating if you don't have examples of run to failure of the component, of the critical component. You might not have sufficient knowledge, information, and data to do predictive maintenance. And then from a business point of view, you must evaluate if it's worth it or not. Okay, the return on investment, the value that prognosis and health management brings you. And again, it can be value from different points of view. Okay, from continuity of production, from the economic value, from reputation also. Okay, so different impacts affect industries, and the people from industry are very well aware of that, especially critical industries. Think about chemical process industry, nuclear industry, airlines industry. Some critical components are critical, and monitoring them is necessary because you really don't want failures, which can be very catastrophic and impact the feeling of all the stakeholders involved with respect to that particular industrial sector. And we can come up with or cite many relevant examples from different industrial sectors, including Deep Horizon from the oil and gas, including the airline accidents, including from the nuclear, okay, where failures and accidents impact significantly the whole industry from various perspectives. What are the typical components that nowadays are at the center of interest because of the opportunity of monitoring them, getting as much KID as possible, and analyzing the KID to develop capabilities of detection, diagnostics, and even prognostics. Bearing, pumps, alternators, turbofan engines in the mobility business, gears, shafts, batteries. These are very common components where it's interesting to evaluate the opportunity of having a KID-driven PSM for predictive maintenance. And of course, there's a lot also the structures. Okay, I'm not talking about structures, we're talking about power components and systems here, but structures are an interesting, okay, dams, bridges, roads, railways, okay, and other structures like that. So now we get to really developing the capabilities of fault detection because we have the relevant knowledge and we're extracting it to detect failures. We got our components and it's monitored, and so we're getting real signal measurements. Now, in fault detection, the objective is to arrive at recognizing and detecting as soon as possible that there's something wrong. Okay. And again, think about the patient of a doctor. And you're taking, the patient is taking blood tests, is taking all kinds of tests, and as soon as possible, you want to detect that there is an illness. Okay. So we got the measurements and we want to define the condition, the state of the component or system. Okay. Well, the typical setting for the fault detection is to build a model, okay, of the component or system as if it were in perfect conditions, so that it gives us in output how the signals, how the blood tests should look like, okay, if the component was perfectly fine. Okay, so they should be blue and behaving like that. But what I'm measuring is the red and it's behaving like that. And so the idea is to recognize small differences, okay, small differences as soon as possible. So not when the signals deviate so clearly, okay, that you could even look at it by eye and it's probably too late, okay. And you have a number of methods that you can use, including auto-associative kernel regression, principal component analysis, the autoencoders from deep learning, okay, that are useful to build this model that, given an input, the actual signals measured, reconstruct, let's say, repairs the signals and tell us how they should look like if the component was doing well, okay? And by the comparison, by the difference, we should be able to detect as soon as possible the abnormal condition. Now, what you have to build this model is data that represent the normal conditions, okay, of your inputs, okay, your parameters of interest, I don't know, pressure and temperature, and you have a number of examples of pairs of pressures and temperatures representative of the functioning of this component in normal conditions, okay? Now, for example, the model that you would like to build is a model based on auto-associative kernel regression, very simple approach, okay, where you feed the model with the signal, the real signal that you're measuring, and you want the in output. So the auto-associative kernel regression is building the function that gives you the corresponding reconstructed values, how they should look like, what values they should have if the component or system was functioning normally. So the data set, okay, is a number of patterns, okay, patterns which are signals measured, okay, on the component and system, different signals, pressure, temperatures at different times, vibrations, okay. So you have an observation, which is a pattern, okay, which is a picture of how the component, of the signals representative of the component in good conditions, in normal conditions, okay. So that's your training data set, okay. Now, that training data set serves you to build the AAKR model that reconstruct the right, the normal signals, the normal signal values. Now you have the model, you enter with a test pattern, which is what you are measuring on with your sensors that are monitoring those variables on your component. And you get a point, okay, you get a what we call a test pattern, okay, and the idea is, okay, I feed the test pattern to the the AAKR model, the auto-associative kernel regression model, it gives me an output, okay, and by the comparison between the reconstructed signals as if the component were normal and the actual value of my signals, I decide if the test pattern is within a normal behavior, a normal condition, or if it's diverging, if it's starting to behave in an anomalous way. Okay, and so here it is. Okay, with the matrix of the training data set, you have built your auto-associative kernel regression, or you have performed your auto-associative kernel regression, which build the function which transmits or which allows you to reconstruct the values of the signals. Okay, you are in business for doing your estimation of the difference between these signals. Auto-associative kernel regression is quite simple. Okay, you are taking the signals of test, okay, that you are observing. So these are the real measurements, okay, and you are building the reconstructed values, okay, by a weighted average, okay, a weighted average of the signals in your training data set. And in this way, this is a weighted average where the weight, okay, is a modulated function of this distance. dk is the distance between the observed real measurement now observed on my component and the examples that I have in my data set, okay? And of course, the distance, okay, which is modulated by a certain parameter here, the bandwidth, but we don't get into these details. But of course, when I compare this input measured on my component now with these normal behavior patterns that I have in my data set, I will give low weight because they're very different. Okay, these I will give higher weight because they're more similar. In order to reconstruct how this should look like, and it should look like a star. This is an example of an application, okay, on a nuclear power plant in a project done with the Halden reactor project in Norway, where we were giving a large number of data simulated by a full-scale simulator of a nuclear power plant in Sweden, where there were 752 sensors and data sampled for 1 year every 10 minutes. Very large data set. We built auto-associative kernel regression models to have our model that reconstruct the signals, how they should look like in normal conditions, and compare them with the signals actually measured. Okay, and this is an example of the signals measured and reconstructed. The red line is one of the signals measured on the plant, actually simulated as measured on the plant. The true signal value is the dot line, okay? The blue line is the reconstructed value by the AAKR. And from the difference, you can identify that there is a sensor's failure because the true value has been reconstructed as the blue line, whereas the measured value, the value given by the sensor is the red line. Okay, and this allows you to identify sensors malfunctions, which is very important in nuclear power plants, both for control and safety reasons, and also for the cost of recalibrating all the sensors during the plant stop for refueling. Okay, and it was a very successful application. Another application, again, on nuclear components is on the reactor coolant pump application done in collaboration with EDF. 48 signals measured for 1 year of data sampled every 30 seconds. The detection of the first seal in the pump, okay, that deteriorates and start leaking, but of course it leaks very little. And of course, it's a very relevant component, okay? So detecting early seal deterioration and small seal leakages is very important. And this is an example of the residuals between the real measurements and the reconstructed measurements as if when the component is in normal condition, when the seal is not leaking, and you see a trend which allows you to detect soon that something is wrong. And based on this detection of the condition of the seal, you initiate a maintenance procedure. So it enables condition-based maintenance. But we've been discussing about KID, and all these examples have been relevant to data only. Actually, no. Knowledge and data, for example, for detection, okay, very nice. In this case, let's consider an example of an electrohydraulic servo actuator, which is a quite safety critical system on airplanes, okay. A failure of these servo actuators requires that the airplane does not fly, the airplane stop right away because the engine stalls, okay? So you want to detect as soon as possible an anomaly on these components, on these systems. Now, we got data, okay? Data from pre-free flight tests, okay, made in the lab, and you get data, for example, on position, current, and other components. Okay, why not training a model for detection, in this case an autoencoder, okay, which fed by the real signal measurements gives you the reconstructed signal as it should look like if the electrohydraulic servo actuator was perfectly fine, perfectly normal, okay? And we train the autoencoder with the available data patterns by minimizing an error between, so by minimizing the error between the reconstruction, x hat t, and the real measurement, so that we get a good reconstruction of the normal behavior of the component. Okay, but it's also known for this particular component that the signals have physical relations, okay? And when the electrohydraulic servo actuator is behaving normally, well, okay, is healthy, there is a relation, for example, between the velocity and the current measured, okay? Well, how do I inject this knowledge into my autoencoder so that the reconstructed signal performs better, because it is also trained, if I can say that, trained to respect the physical relationship between, for example, velocity and current. Well, I add another error function, another loss function, okay? I don't want only to minimize the difference between the real measurement when the component is normal and its reconstruction, but I also want to award minimize or to penalize, if I may say it that way, to penalize the reconstruction which are outside, so they do not respect the physical relationship, okay? And I want to minimize, therefore, the reconstruction that are not on the region of normal operation, the physical region of normal operation, in this case between velocity and current. And these are the results that have been obtained in this application, where you see the typical truth table for the detection, okay? And you have false alarms and misalarms rate, and you see the improvement when you actually are also considering the physical knowledge of the behavior of your variables, of your relevant variables, and with respect to the less performing or less precise performance of an autoencoder, which only minimizing the error of the reconstruction, okay, and not penalizing the conformation with the physics behind the behavior of the system. Detection we take care of. So now we can move to fault diagnostics. Okay, fault diagnostics, again, we got our components, we're measuring signals, and we want to be able to associate, to label the signals that we are measuring with a state of the component of the system. Again, it's the patient which is taking particular medical exams, goes to the doctor, and the doctor says, you're doing good, no problem, keep living that way, or you have this particular illness, you have this particular other illness, and so on. Okay, so we want to build an empirical classifier, and there are quite a number of approaches that can be used, from the simple k-nearest neighbor approach to the support vector machines to a number of neural networks that can perform that task. Now, the data, okay, beautiful data that we have is the signals measured and colored, so labeled with respect to the class they belong to. For example, I don't know, this is a healthy class, so as long as the signals we measure fall in this cluster, we are doing good. But if we see that the medical examinations and the parameters that we are monitoring fall here, then it's degraded in a certain way, or it's a certain fatal mode, and the same for this. Okay. Now, with this, we can build easily, for example, a classifier based on the k-nearest neighbor. Very simple. Okay. Measure signals. We must associate the specific class to which these signals represent the signals allocate the condition of the component or system. So just a very simple example. Okay, suppose that these are your patterns that you know the class of membership. Okay, so these are training patterns where you know that this pattern corresponds when the signal values are at these levels, they are class 1. When they are at this level, they are class 2. When they are in this area, in this region of the plane, signal 1, signal 2, they are class 3, okay? And then you have your current state of your component or system, which is the red dot, okay? Signal 1 has this value, and signal 2 has this value. Well, in this case, okay, you decide to look at the 5 nearest neighbors, and this is a very trivial representation, of course, but you see that the majority, by majority vote, you have 3 of the nearest neighbors, which are the nearest, by the way, okay, so they really are the nearest among the 5, and there are 3, and they are of class 3, whereas there are 2 others which are near, but not as near, and they are of class 2, and therefore you say, okay, you know what, this my component currently is in state 3, whatever that state 3 illness is, or degradation level is, or if it's healthy, okay, you do it that way. Now, this is beautiful. What do we meet in practice, however? First of all, in practice, the normal situation is that we have patterns, we are measuring, monitoring data, but we don't have the labels. We have no idea if this is the right, healthy, what the degradation is this, what degradation is this. Okay, we are measuring data, but very often we are not able to associate the actual state of the component or system. Here's an example of how we deal with this. You move to clustering, to really data clustering. So here is an example of an application where we had 149 shutdown transients from different nuclear power plants. Transients are very rich in information if there is an anomaly or a malfunction of some components. There were 12 signals characterizing these shutdown transients. 5 were related to operation, and 7 were related to the actual turbine behavior. Okay, so internal turbine behavior. But there were no labels on the large amount of data. 149 shutdown transients, it's a rich data set. Okay, and by applying some clustering, a combination of clustering approaches, we were able to identify actually 5 different classes of behavior of components, one of which was related to healthy. A posteriori, okay, with the experts, operators of the plants, we were able to label them in different types of malfunctioning. And this is quite interesting because then it allows you to diagnose the state of the turbines of your plant while observing shutdowns, okay, and defining what you need to do in terms of condition-based maintenance. Not only that, not only we don't have labels, okay, but typically the classes are imbalanced. What does it mean? It means that because engineers do a good job in designing and operating and maintaining components and systems, these components and systems are most of the times in healthy conditions. They are kept and operated in healthy conditions. The signals you are collecting are mostly related to good normal operation. There are very rare degradation data, okay, and also typically you are using data collected from components and systems that are similar and belong to a fleet of plants or production systems and so on. Okay, so how do you handle that? Okay, you got a turbine A, turbine B that gives you different data. Most of them, for example, is this, and it's a good functioning data. How do you combine that? Okay, well, here is an example that's coming actually from mobility, and it's actually an interesting critical example because it's the failure of doors to close, and this, of course, leads to a critical safety problem because people could fall out of the train while the train is running, and this stops the train. Okay, this stops the train cannot service. Okay, so we were challenged to build a classifier to define the different levels of degradation of the doors of a train in order to anticipate and diagnose possible different levels of degradation and therefore intervene before we need to stop the train. Okay, and the situation typically is okay. For example, we got a fleet of trains. We got train A, train B. We are measuring a certain variable, for example, voltage, and for a train, maybe we even have label data, okay, and we have many patterns of healthy behavior because most of the times the doors indeed are operated and maintained so that they're healthy, okay, and we have few patterns of degradation behavior, and then we have a train B which is completely unlabeled, okay. So how do we handle that? Okay, well, first of all, we need to try to bring together the data from the different elements in the fleet, from the different trains in this case, so that we can treat it the same way and we can classify the states of the systems in the same feature space. This calls for domain adaptation, where we can treat the information coming from A and B in the same way and exploit it all, okay, exploit it all to build our classifier, okay, so that when we get, for example, a new unlabeled trend behavior of our voltage measured on train B, okay, thanks to the fact of having used a training data set from both A and B, we're able to say, okay, look, it's certainly an anomalous behavior, certainly a class 3 situation for your train B currently, okay? Now, this was quite challenging to develop. First of all, we had to, excuse me, to proceed to extract the features where we can project the information on a train A and train B, so that the classifier makes the minimum error in the diagnose of the state of the component. healthy, the door, okay, healthy or degradation type 1, type 2, type 3. Okay, so there really we are in what we were talking about just now, minimizing the classification error, so that we are able to confidently assign data collected on the train to the right class, in this case, class red, okay, class red. But then we have train A and train B, and we want to make sure that the features are indeed representative of the state of both A and B in terms of the diagnosis. So we are actually doing some adversarial learning on a domain discriminator to cheat it, okay, to try to cheat it as much as possible, so that the train A and train B characteristics are as similar as possible in the feature space that we have extracted, okay? So that now the features that we extracted are indeed good for both A and B, and the classifier is accurate in its assignment of the class. This was applied on real data, okay, with a significant improvement, okay, of the classification accuracy by the classifier method, where the features have been calibrated through, let's say, in a sense, through adversarial domain adaptation, okay, with a significant improvement. And finally, the dream, okay, finally the dream, prediction. We are at a certain time, okay, with our component, we have a kid, we're able to observe and track a certain degradation pattern, okay. We arrive at detecting that something is going on because the trend has, or the degradation has overcome a certain threshold, okay. And now we want to say, okay, well, okay, something's going on wrong, okay. There's an anomaly. How long do we have to intervene, to do something, okay? And this is a very, very relevant information. How much useful life I still have? Can I wait until the next stop of my component and system, my train, my nuclear power plant, because anyway I need to do something else? Can I wait until the peak hours of production are over, because then the impact of stopping for doing the maintenance will be less? So very important, being able to estimate or predict the remaining useful life, okay? Kid driven, okay, say data driven or kid driven more precisely, okay, very good. Now, an example, steam generators, a fundamental critical component, big component in nuclear power plants, okay? They degrade, they're subject to certain mechanisms of clogging and fouling, okay? And this can lead to the need for stopping the plant. Maintenance interventions can be performed mechanically by removing some of the deposit that clogs the tube support plates, or going through chemical cleaning, which is much more expensive, okay, much more expensive, and requires to stop the plant, to take care of the cleaning, and then to reinitiate the operation of the plant. Now, in this case, we had different types of data and information, okay? There are numerical data related to the time from last inspection, the number of chemical cleanings that have been performed, the number of mechanical cleanings that have been performed. Data are measured, physical data are measured on the steam generator, flow rates, mass flow rates, temperatures, pressures, okay? And then there are inspection reports that tell you by non-destructive testing and maintenance intervention how the tubes of the steam generator conditions are. So imagine that now you are here, okay, and you have your steam generator has lived this life where there has been a number of non-destructive inspections. Then there has been some mechanical cleaning, okay, because we were over the threshold of logging that would require mechanical cleaning. In one case, we did chemical cleaning, and you have the text reports of how it was done. You have images, you have transients, and from here, you want to predict when you need the next inspection, when you will need the next mechanical cleaning, when you will need the next chemical cleaning. Quite a challenging and interesting problem, okay? We dealt with this by a multi-branching deep neural network approach, where we had one development to extract the features from the numerical signals, one from the text by using natural language processes through word embedding, and then the images of the transients of the signals. And we extracted features from the meaningful content of the different types, okay, of sources of data and information, and then we put them together. So the features were then the concatenation of the features that were the best squeezed out knowledge from the numerical values, from the images, and from the text. And then we built a regression layer for the degradation prediction, okay? And here are the results, okay? The proposed method has a mean square error on the prediction of the next time to of inspection, okay? By combining all three sources of information, whereas you have a less performing result in case of using the two best sources of information, okay, text and data. And if you use only one source of information, the best model with only one source of information, which in our case was the text, you will get an even worse performance of your prediction of next inspection time, okay? Very interesting approach. Now, again, the data, when you look at the data on the KID for predicting the remaining useful life, so you're actually predicting from today, okay, from the present time, when the time of failure will be. One issue that is coming from, that luckily is coming from practice and from industry, is that you have very few run to failure trajectories because, and I repeated what I said before, engineers do a good job in designing components and systems so that they do not fail, operating them so that they do not fail, maintaining them so that they do not fail. So you have few examples of your degradation indicator, of your health indicator that arrive at failure. And this is challenging, okay? And we met this challenge, for example, in the predictive maintenance or the prognostics of failures for lithium-ion batteries, which of course, you know, are extremely interesting nowadays for the industrial sector, okay? It's quite important. There's a lot of interest in avoiding failures, detecting anomalies, diagnosing anomalies, and predicting the remaining useful life so that we know how much we can still use the battery for our purposes. Now, in field applications, you have the use, you have the signals measured on the in-field use of your battery under changing environments, okay? And typically, degradation is not measurable, okay? And very few of the trajectories that you have of behavior of your battery are led all the way to failures. You replace it before, you have ways to know that it's going to degrade or fail, and therefore you have incomplete trajectories of the signals of the KID that you're measuring on the battery. On the contrary, a lot of efforts are being done on the laboratory to characterize the battery behavior also in terms of degradation. And in that case, okay, in controlled environment, so not in a changing environment, in controlled environment, you have signals that allow you, signals measured all the way all the way to the end of the life of the component, and you can build a degradation indicator and see the pattern of degradation all the way to failure. So you can generate a number of patterns for your training data set for building a predictive model with run to failure data, but they are in a specific controlled environment of laboratory, which is different from the in-field application. So how do you handle that? Well, again, that calls for, and in our case, we had a situation where, therefore, we had information from the controlled environment of the lab of different degradations for measuring the signals. Okay, we know the signals and we know the label that these signals correspond to, healthy, non-healthy, and so on. From the in-field, okay, we have some measurements of the signals, but we don't know, okay, the level of degradation. Okay? We don't know the level of degradation. So we do a first domain adaptation model that exploits this information to construct the degradation level in the in-field conditions. Okay, and then we use these reconstructed reconstructed degradation levels for the in-field, also for the in-field applications, and the lab information, which is complete of signal values and corresponding degradation levels, to build our remaining useful life prediction model. Now, maybe here, I'm not sure, I might be running out of time, so I will either go fast or skip a little bit.
Oh, we are good.
Yeah.
But
okay.
if you want to wrap up, it's also okay. Thank you.
Okay. Well, okay. Just okay. We have a first encoder that puts together this heterogeneous data, because this is a three-dimensional data where you have also the degradation, not only the signals that you're measuring in the controlled lab domain. Here you have only the signal values. Okay. We build a first encoder that puts together and finds the structure, the features that enables them to reconstruct eventually with a regressor the values of the degradation, okay, corresponding to the signal value. So we have also labeled also these data. Now we have this data labeled in lab, this data labeled to the degradation corresponding to the in-field operation of the battery. We put this together, okay, building a loss function, okay, to actually we build now the long short-term memory application to finally actually be able to predict the degradation. Okay, and here it is, the remaining useful life. Okay, and the results, okay, are shown here, where here you see, here are the synthetic results in terms of accuracy, okay, of the prediction of the remaining useful life. Here's an example on one test battery where here is time that goes by, actually cycles, okay, charge cycles, okay, recharge cycles. And here, of course, the remaining useful life goes down, okay, as you keep recycling or recharging, sorry, okay. And here are the different predictions, okay, where our heterogeneous transfer learning model is the blue one, is the most accurate with respect to other state-of-the-art methods that can be applied here. And overall, the cumulative accuracy is much larger than with the other domain adaptation and homogeneous, though, okay, without the use of the in-field source domain, and the LSTM only based on the lab data. But okay, prediction, of course, it's has somehow a magic touch. I mean, we are as properly as possible looking into a crystal ball to predict the degradation behavior of our components and system in the future. So it is fair to say that if I build my predictive model, okay, which magically tells me, hey, 57 hours, 25 minutes, 18 seconds. Before that, you must change your component because at that time it will fail deterministically at that time. Okay, it's hard to believe it. Okay, that given the uncertainties around our behavior, the behavior of our component, the knowledge that we have from the kid, okay, as big of a kid as we have, we're collecting data, but not infinite data. We're taking images, we're looking at the text. There's a lot of uncertainty associated to the observations that we make. The degradation process evolves in terms of a stochastic process. Certainly, there is a changing environment that's going to influence how the degradation will evolve because of external and operational conditions. And then we're building a model with all this knowledge that we have, which is a model. So it's not reality. There will always be a gap to which uncertainty is associated. So we need to develop a prognostic model that actually gives us not a point estimate of the remaining useful life, but it will give us an expression also of the uncertainty, or if you wish, the confidence associated to that prediction. Okay, and so it will be much more acceptable that an output will come in terms of we can expect that the component will fail between 72 and 84 hours, and my confidence in it is 95%. Okay, and there are ways to develop this bootstrapped ensemble of models where you combine different models that give you different predictions, and these accounts allow for some of the uncertainties, and you can compute the uncertainties. Monte Carlo dropout is another approach that allows for doing that. It's not just a point value prediction, it's a best estimate with the associated uncertainty band, uncertainty evaluation. With that, you arrive at decision making. Okay, you got your component, you collect and extract data. KID, you get your relevant knowledge out of that, and you do the decision making. Now, the decision making, of course, is partly informed by your efforts in prognostics and health management, which is using all the KID that you have to tell you something about the future evolution of the degradation, to estimate or predict your remaining useful life. But of course, your decision making, as we were anticipating before, on when to do maintenance is also constrained by a number of objectives and physical constraints that you want to achieve. And it must be informed also on what drives these objectives and constraints. Okay, as I said, user demand, peak hours, weather conditions. So you don't want to do maintenance on your air conditioning when it's quite hot outside. Energy price nowadays, that there's an energy market. Okay, resource availability. Okay, so you got also a predictive analytic effort to be done also on the conditions and factors that influence your decision. So your decision on when it's best to do maintenance. Define your maintenance policy on the basis of what's happening to the state of your component and system, but also on the basis of other factors that influence your production needs, production objectives, and influence the use of your products. There are challenges in that, okay? There's challenges in that related to what becomes a dynamic decision-making for maintenance, because now we're saying, I'm not scheduling the repair or the inspection and maintenance on my car once a year before I go on summer vacation, okay? I just do it based on condition or on prediction of the remaining useful life based on PHM, and including also a number of other aspects that factor in my decision. But now, if my prediction tells me that tomorrow I need to service my car, and tomorrow I have a business appointment, a love appointment, I need to go on vacation, and I go to the mechanics and he tells me, sorry, your Ferrari needs to wait because I have 5 Fiats which are waiting for their repairs, and I don't have the parts for your Ferrari. Don't forget that Italians professor always have a Ferrari, so the problem is serious. And so you're not, resources are not available for your maintenance effort. So planning dynamically the maintenance is not trivial, absolutely not trivial from a logistic point of view, from spare parts management, for logistics management. Okay, the train comes to the depot. Okay, you take the data, you analyze it, do condition informed condition-based maintenance or prediction of the remaining useful life. The door is going to break in the next trip. Okay, so you need to service this tonight. Well, but I don't have the guy that can do it. I don't have the spare part of the door to change it, so I need to block the train. Okay, very difficult. And then, of course, the degradation and the maintenance behavior, or the degradation behavior of the components and systems is influenced by operationals. Operation and maintenance go together. If I operate and stress the components in a certain way, degradation might be faster or slower, and it might be convenient to integrate the whole picture and maybe slow down some production in certain times when I don't have peak demands or other things, and my component is relaxing and is not as stressed, and its life will be longer, its degradation will be slower. Very difficult also challenge to be met from an industrial point of view. Finally, if you're still with me and I've not degraded you too much, okay, I come to the conclusions, okay. Great opportunity, okay, from the kid and from nurturing the kid, from looking into the kid and enabling prognostics and health management for predictive maintenance. Lots of developments and deployments have been done on treating these signals, these images, and these texts to enable, in particular, detection, diagnostics, and some prognostics and prediction of remaining useful life. Of course, there's a lot of work done also in the prediction of future use, user demand, weather conditions, energy price, and so on. So there are the ingredients to optimize our operation and maintenance integrated. Okay, the optimization, it's a very complicated and hard problem. Okay, that receives quite heterogeneous inputs and needs to come out with the best times to operate in the best way and maintain in the best way, doing the right operation and maintenance at the right time. And this requires a dynamic deployment of the results of the policies of operation and maintenance in terms of managing the work orders, the supply chain, the part management, the workforce, and so on. Fascinating scenario for industry. Now we are working on enabling the optimization under these integrated and multi-factors conditions. Okay, in particular using reinforcement learning, which of course is it has great potential. It also has quite numerous challenges in terms of computation. Okay, and the vision. Okay, the vision is for management of power asset is really ambitious in the sense that okay, you got your system that you need to maintain, your asset you need to maintain. For example, offshore wind turbines. Okay, you got your fleet of operators that can go and maintain, and you want to optimally deliver the maintenance, to the red failing components and also anticipate and take care of the yellow ones before they become red in an optimal way of operation and maintenance, as we mentioned before. For that, you need, of course, to make sure that you include the factors that influence your decisions, not just the degradation state predictions, the remaining useful life prediction, but as we mentioned before, also the other factors which include weather prediction, because you don't want to go when the weather is good for wind and you're producing a lot. It's the energy price tells you to keep producing and not interrupting anything, because you're selling, even though you are producing less, you're selling it more. And then there is the user demand prediction. This is clearly a very critical issue. Okay, for example, okay, and this is very important in Europe and in particular in Italy nowadays. You have the Champions League soccer semi-finals, where the two teams in Milano are playing at the stadium, and you will have probably close to 56 million people watching the game and using their mobile phones to exchange bad luck to each other. And this is a very constraining condition that requires you to have been managing very efficiently your operation and management of your power asset, and accounting for all the uncertainty in your prediction. And with this, I thank you very much for the opportunity again. I hope I was sufficiently clear and hopefully a little bit interesting. Here are my contacts, and I close by thanking, of course, all the collaborators from these groups. In particular, of course, I would like to mention Professor Piero Baraldi, who is quite an expert in this field, and he has helped me a lot in developing this vision and the presentation of this topic, if I can call it that way. Thank you very much.
Thank you, Enrico. This is a great presentation, I will say. Yeah, I like how you review the fundamentals of health monitoring in power systems, and how you show amazingly machine learning methods can easily get into the territory. And finally, the visualization, the data you got is eye-opening to me, because I have been doing these fault detection and health monitoring for a while. Without any further delay, I want to pass some questions to you. Number one, so John Dirkman said, this is a great presentation. Yeah, he has a question. How do you think the PHM will continue to evolve in the future? So John is from the industrial background. So yeah, if you can give us your thoughts, that's nice.
Yes, yes. Thank you very much. I think that the PHM is going to evolve in practice by, on one side, if I can say, providing results. And I expect that this will continue in particular on the detection and diagnosis of critical components, and the results will be very useful for managing safely, operating, if I can say, operating and managing safely and effectively production components and systems. That requires the development of the design of the proper architectures of PHM specifics for the different cases, and this includes also the further development of the ways that data are collected, even in terms of allocation of sensors and frequency of measurement. So there's a hardware part that needs to be consolidated to specific applications in the practice of PHM, and then and I hope that the conclusions conveyed this message. PHM cannot be left per se alone. Okay, if it doesn't inform a decision, it's not so useful. Okay, it's not very useful. So it must assist a decision on what to do and when. Okay, so there are aspects of decision making which not necessarily now we must think of completing it in terms of integrating also the aspects of operation and optimizing with respect to the semi-final of the World Cup. But anyway, adding some value to the decision making that is done for maintenance. That needs to be continuously pursued in the field. From the method point of view, I think that there will be a continuation of development of methods, particularly in trying to inject more things, okay, physical knowledge, heterogeneous data sources, text, data, images, how do you combine that, making also the models for certain applications as explainable as possible, understanding why they give you a certain answer, why are they diagnosing that anomaly, what is the reasoning behind it, because in certain applications, I don't necessarily want to completely rely on a black box to assist me. Okay, I want to ask the doctor, how did you come? Please explain me. How did you come to the conclusion that I have this problem, and you're giving me this medicine? So okay. I see these two strong continuation. Sorry.
Nice. And there's a following up questions from the students. So, you have nice data sets for student study. How do you have any suggestion that where they can find something either realistic or simulated so that they can just try something?
Yes. I'd like to suggest that a student that wants to understand a method and then think about how he can improve it, and he or she can improve it and develop it further. Right. I would say start from a case study that you build yourself and it's completely in your control. Generate your data, even from statistical distribution, from time series. There are mathematical time series, but that you completely control it and you understand and are able to interpret the results of the method, if it's reasonable or not. And you can inject changes, anomalies, and so on. Then then depending on the application, try to make this simulated artificial case study having the characteristics as much as possible of the case that you want to treat, or the real case that you want to treat. So make sure that it has the ingredients and the components or the elements that are representative of what you expect on the signals and data and knowledge that you have in the real case. Then rely also on benchmark data. Okay, literature benchmark data is very useful. Most of it is from laboratory experiments, okay, but there are quite a number of laboratory experiments and data challenges that are quite interesting. And then, of course, to have the real data, there's no, I mean, it has to be a project in partnership with some industry that is ready to give you the data. And often, if you can go to the industry by showing to them the results that you have obtained on your developed case studies that resemble what happens in their industry, and convince them that that's a good opportunity to develop together the method. And if you get a project, remember me and give me some of the money from the project.
Okay, that's nice. And the next question comes from Bing Wang from WUT. He or she says, "Thank you for your excellent presentation. I would like to raise a question. How to verify the correctness of the reliable or reliability model or risk model in case of insufficient data. So when you have insufficient data and we are still proposing some machine learning methods for reliability, then do you have any suggestion how to verify if such a model we use it or we don't want to use it? Like, yeah.
Right. I mean, I think that the testing on simulated data, on lab data, so it's a process. Okay, so you test and consolidate the accuracy and the performance of your PSM technique, if we're talking about PSM, because I think that the question was extending also to risk and reliability, which is farther down the path. But remaining on PSM and this machine learning artificial intelligence method, it's really a path. And of course, you want to make sure that you validate it through a progressive testing on the different types of data that you have, simulated, lab, and then in the field. And then, as much as possible, make sure that you have a filtering method that takes the input that you are providing when you're using the PSM. You're giving some input data. Make sure that you are able to catch if that data indeed belongs to the space that you have been training your method for during training, and you're not outside of that space of knowledge, information, and data that you give into the models, because otherwise you would be forcing extrapolation to your method, and you're risking to get wrong results. And there are ways, of course, to do this filtering of the data and information and knowledge to make sure that you are dealing with a situation that is within the baggage of kid that your techniques have been developed on.
Nice, thank you. And for the next, Professor Qiushi Cui from Chongqing University would like to ask you, when evaluating the maintenance plan of a particular equipment, let's say a hydro plant, what is your suggestion to quantify different kinds of fault degrees, as well as the equipment condition? I guess I can interpret it in a better way. So today you talk about there are different faults, maybe different cases, but for each of them, maybe bad things happen. But do you have any suggestion on how to evaluate the degree, like how bad it is?
Okay, well, I mean, I think that that comes in a sense with the problem of unlabeled levels of degradation or classes of degradation. So I think that already the initial necessary result is to distinguish from the signals measured and maybe even the text and the images. So from the KID, okay, distinguishing different clusters, different families of behavior of the components. Then inevitably, to label them, typically you need to resort to experts, okay, to try to understand if and what level of degradation these signals clusters or clusters of signals are representing, or having techniques that render explainable the clustering in some ways and extract some information on the degradation level.
Okay, that's nice.
And work is being done and is under process on trying to explaining these differences in cluster behaviors.
Yeah, I also learned that from your unlabeled data, how do you do quantification, how to use data properties and behavior.
Exactly.
Okay, all right. The last question will come from me. I work in power protection, but for power system protection and we are kind of conservative. So when there's a new paper saying machine learning is going to help power system to trip a line or maybe to do a better protection, people say there's no guarantee, and what if it's bad? So you are expert on this like fault analysis, diagnosis, and maintenance. Can you give us maybe some idea, or maybe the society some guidance? Should we just try it, even when there's, not perfect confidence? If we try it, how should we try it when we know sometimes maybe it will give us a disaster? Should we just stop trying maybe AI for protection? Any idea is appreciated from your rich experience.
Well, if I can formulate in a sense out of the blue my answer, I would say in all critical applications,
right.
First of all, AI, predictive AI, or let's say BHM, should be on one side used as an assistant, not as a decision maker. Okay, so
right.
it's an added teammate. Okay, that is able to do. It's a good teammate. Okay, it's quite a strong player because it's able to process much more data, much more signals, and in a different way in which you are processing it, and so it gives you different perspectives. I go back to, as much as possible, not just since he's a strong, good teammate, believe it blindly, blackly, okay, but building capabilities to interpret as much as possible why it arrived at the conclusion that you need to trip the line, okay. So that certainly is something that I would be equipping, and I would be asking to develop, okay.
Yes.
I don't want a black box, okay,
right,
for that particular application. And then finally, I would probably insert the verified performance in terms of the final accuracy, the final probability of missed alarms or false alarms within a system risk analysis. Okay, because at that point I have a probability of that assistant giving me a bad assistance. Okay, but how many times it saves the day? Okay, because it's giving me the right good alert, alarm, and assist me in tripping the thing. And I want to see the overall gain on the system risk.
Right. I see. That's great. Thank you so much. And I agree with you. It's a great teammate. We probably don't want to rely on him completely, but rich information, why not put it on to the table to look into when we are making the decision? Okay, so thank you so much, Enrico. We appreciate your time. On behalf of the Power and Energy Society and our subcommittee for machine learning for power systems, we will follow up with you on the website design, material collection, so that more students and industrial members can learn from you.